in terms of rows, you go for I is equal to 1, and then you go through the first row of A, and then you pick I is equal to 2, and then you go through the second row of A, next row, and so on until you get to the nth row. Whereas in the second program fragment, you go through the array in columns. You pick the first column, j is equal to 1, and then you go through the entire column of A, the first one, and then you have j is equal to 2 that defines the second column of the array, and so on and so forth. And if you have a situation where the array does not fit into main memory and you need to use virtual memory management, then of course the question of the mapping function arises. How is the array A mapped into the main memory space? And if it is done in terms of rows, then you have established, I hope, in everyone, that the first version, which does according to the visit of the array, is in terms of rows. In the case of row major mapping, that is the efficient one, and the second, where the access to the array is in terms of columns, is the inefficient one. Similarly, if the memory mapping function is in terms of columns, it is the second program fragment that is efficient, and the first one that isn't. Now, it turns out that this can be done automatically. There are compilers, high-performance compilers, that carry out dependence analysis. They basically determine that there are no dependencies, and in that particular case, the compiler can automatically determine that, well, we're using, say, column major mapping, and this is what the programmer wrote. But using the fact that there are no dependencies among the array elements allows us to transform the first program fragment into the second program fragment. The second program fragment, as we've said, is much better in terms of using virtual memory management in the case of column major mapping. So even though the programmer wrote an inefficient version that does to some extent clash with the memory mapping function, column major rather than row major, even though the axis, of course, of the first program fragment is in terms of rows, the high-performance compiler can carry out that dependence analysis, and on the basis of that dependence analysis can then transform the first version of the program fragment into a completely equivalent second version of the program fragment, which is much, much more efficient in the context of virtual memory management if the mapping function of the main memory from the array to the main memory is in terms of columns. Now, that is, of course, an observation that is crucially dependent on the fact that there are no dependencies. Let's look at another version, program fragment. Let's just assume we have an array B from 1 to n. and we do b, I'm sorry, let's do I from 2 to n, just to be safe. Bi is bi minus 1 times 2. Well, in this particular case, there obviously is a dependence from B1 to B2, and a dependence from B2 to B3, and a dependence from B3 to B4, and so on until Bn minus 1 to Bn. So if I had done the same thing that we did up here, where we didn't have any dependencies, and I transform this to that, or in fact I could change the way in which the indices are being done. I could go from n to n minus 1 to n minus 2 to 2 to 1. That still would be entirely correct. But if I did that backwards here, I get something totally different. I'm sorry, this is 2. Come on. 2. And so if I did the same thing, bi is bi minus 1 times 2, I will have a very, very different program. These two are not equivalent. Why? Well, what do I get here? B2 is going to be B1 times 2. And B3 is going to be B1 times 2 to the power of 2. And in fact, Bi in general in the first program fragment is B1 times 2 to the power of I minus 1. So Bi is B1 times 2 to the I minus 1. You can calculate that. That follows directly from carrying out this program fragment. Whereas here, it's going to be very different. Bi, well, Bn is going to be Bn minus 1 times 2. And Bn minus 1 times 2 is going to be Bn minus 2 times 2. So this is very, very different. Basically, you take Bn and that becomes twice the one before, and then that one becomes twice the one before, and then that one becomes twice the one before, and so on and so forth. So obviously in this case, in the first program fragment, the only thing that is determining things is B1, and everything else then is a product of B1 and a power of 2. In the case of that second program fragment, where we go basically backwards through these indices, this is going to be radically different. So these are not the same, but up here they are the same. And so the fact that we're able to determine whether something can be done or not, whether a transformation can be done or not, is strictly dependent on the dependencies between the variables, the variables that we manipulate in a program. And that in turn implies that we effectively have to deal with a mathematical algorithmic regime that determines whether there exist dependencies. Now, as I have indicated, dependence analysis requires a good deal of analysis. It is non-trivial, but it can be carried out reasonably accurately. And of course, when I say accurately, I am not suggesting that we ignore dependencies. That would be fatal. I'm simply saying that there may be situations where the dependence analysis module is not certain whether there is a dependence or not. And if it is not certain that there is no dependence, then it will assume by default that there is a dependence. Because what really happens with a dependence is that it impedes a transformation. So in this particular case, from the first to the second program fragment, it is clear that there are no dependencies, and therefore we can go back and forth depending on what is better. Now, in the second case, the array B, it is clear that there are dependencies, and therefore there would not be any way of transforming that first version into the second version because they're completely different in their results. And so that kind of thing can be done automatically, and then the compiler can in fact carry out that transformation from one code fragment into another one, assuming, of course, that one of those two code fragments is in some sense better, more efficient than the other one. So you obviously want to go to a code fragment that is more efficient as opposed to a code fragment that is less efficient, assuming, of course, that both of them are equivalent. So that would be the case in the case of the initialization of the array A, but it certainly wouldn't be the case in the second example, where we assign values to that array B, Bi. In this case, it does not work because it is incorrect to transform one into the other. And so that is the kind of thing that can be done. Most of your compilers probably do not do that kind of thing because dependence analysis can be quite expensive. So for the most part, you probably would expect a compile that may be a few seconds, maybe 20 seconds, 10 seconds, 20 seconds. If you do a careful dependence analysis in order to be able to determine whether some program fragment can be transformed into another, presumably more efficient program fragment to execute, that could very well then take 30 minutes. And most of you probably are not really that interested in being that efficient, especially when you have to wait for half an hour to get the result of your compile. So there is an example carried out on pages 129 through 133. 33. You can look at those. That gives you a little bit more of an example to illustrate that. For the most part, this is not the kind of thing that would be expected of a programmer. The typical application area of dependence analyses are, as I said, in high-performance compilers, where the objective is vectorization or parallelization of a program. Although, as you can see from the examples that I gave on those pages 129 through 133, in the case of the use of virtual memory management, it may well be that you can do these things by hand and then reduce the amount of pages that will have to be retrieved from external memory in order to make your program more efficient. I remind you that virtual memory management tends to be very inefficient in terms of the time that it takes to do it. And so if you can reduce the number of pages that have to be retrieved from external memory, you are going to end up with a more efficient program. And so in some cases, you may well be able to do that manually and obtain a program that is much more efficient than what you would have what you would have obtained otherwise. Are there any questions about that? So the next topic then is recursion and space complexity. We've already touched upon that in some contexts, especially when I pointed out that the space that the recursion stack requires has to be counted into the space complexity of a program. So what that means is, of course, that effectively, if you require space for a stack, a recursion stack, then that space has to be available. And it has to be made available, it has to be set aside in order to be used. And the important upshot of that is, of course, that in general, it probably makes very little sense to consider average space complexity. You can, of course, do it, assuming you have a probability distribution for what amounts to average. But the fundamental fallacy in this analysis is that if you are wrong, and you are most likely wrong in some instances, because that's what average is all about. If you're wrong, what do you, and you need actually more space than you allocated for the stack, what is going to happen with your program?
It's going to crash.
It's going to crash. That is the stark reality. If you don't have enough space, and important for the stack, for the recursion stack, because you assumed you have an average case rather than the worst case, your program is going to crash. Now, this is fundamentally different from what happens with time complexity. If you are wrong and you assumed it is average time complexity, in fact, it is not average, it is worse than that, you'll just have to wait longer. Your program still will terminate properly with the correct result. It may take longer than you care for, and it is conceivable that you are getting tired of waiting for the program to finish, in which case you might explicitly abort the program. That's neither here nor there. But if you just let the program run its course, it will terminate normally. In the case of being wrong on the space complexity, because your average case does not account for the space that is required in the worst case, your program will not terminate normally. It will terminate abnormally. It will crash, which is, of course, a fundamentally different situation from what you have when you are wrong with your time complexity. And so what that really then means is that for all practical purposes, it really doesn't make a whole lot of sense to consider average space complexity. It's a bad idea. Average space complexity. And so where does that leave us with something like quicksort? Well, quicksort, of course, as you probably have heard in previous courses, has good press. And so I am trying to set the record straight. Personally, I do not think that quicksort is an attractive sorting algorithm. Why? Well, because of the various complexity issues. Quicksort is, of course, quite fast if you're lucky. Its average space time complexity is in log n with a quite small constant hidden in the order of notation. And it does require, even in the case of you being lucky, it still requires a stack that is order of log n. So it is certainly not competitive with, say, heap sort, which is, of course, a sorting algorithm that requires constant amount of space. But it is worse than that for quicksort, because if you are unlucky, then your space complexity is order of n, because your stack can get order of n in size, and so the amount of space in each initiation record is constant, so you have a number of items that have to be stored there, and then that amounts to order of log n. Order of n space for quicksort in the worst case. And now, of course, we should step back and say, well, if we are willing to set aside that much space, which we really should if we get away from the average space complexity and look at the worst case space complexity, then we actually are going to be much better off with merge sort, because merge sort requires an additional array. So it is basically n plus order of 1 for the various runtime variables that you need to control things, but that's only order of 1 in space. So altogether, you have order of n space for merge sort, but the constant there is typically smaller in the order of space complexity, because the n is really with just one, this constant one, whereas the activation record of in a stack is on the order of, well, 5 or 7, depending on how it's actually going to be implemented. So this is a factor that is much, much bigger than for merge sort, where it is n plus order of 1. So the average space complexity of quicksort is not really a very good idea. The issue here is that if we have quicksort, we should look at the worst case, which is order of n. And in addition to that, the time complexity, this is, of course, space complexity. The time complexity for quicksort in the worst case is n squared. You know that. And so if you are willing to accept that you require order of n space, then merge sort is overall a much, much better algorithm. It is a little slower than, just about same for average time complexity, but of course its worst case time complexity is still only n log n, whereas quicksort is n squared, and that means that overall the time complexity is much better for merge sort than for quicksort. And on the other hand, if you're horrified at the idea of having to set aside order of n space for sorting in numbers, then you should go with heap sort, because heap sort is again guaranteed to be n log n time complexity, best case, worst case, average case, and it requires only order of 1 space. So it is true that the constant that is hidden in the order of notation for time in heap sort is a little bigger, maybe twice that of the average quicksort time complexity. But in the worst case, of course, it's still only n log n for heap sort, but for quicksort it's n squared. So that means I would argue that for sorting, if you have space, order of n space available, I would go with merge sort. And if you don't have order of n space, I would go with heap sort, because both of these are guaranteed to be n log n worst case time complexity, which quicksort is not. So that's, of course, summarized in the table on page 144 that clearly indicates where you are with the various complexities. I define here what I call prudent space complexity. Prudent space complexity, of course, typically is the worst case space complexity. And so quicksort has prudent space complexity order of n, which is similar to merge sort, whereas heap sort, of course, is order of 1. Any questions about that topic concerning space complexity? So it's illustrated with quicksort, but of course the general conclusion here is that in any instance, average space complexity is a bad idea. You really should always consider worst case space complexity, because the consequences of being wrong with space is the consequences are much worse than with time. With time, you just have to wait longer, which presumably is not going to be the end of the world if you do it prudently. Obviously, you don't really want to have a nuclear power plant control system that assumes that everything is average, or a fly-by-wire airplane. So in that case, you really want to have things geared to worst-case complexity. But if you do something like a payroll program, well, if it is takes half an hour longer, the end of the world is not going to happen. You just have to wait a little longer. In the case of space, the program may crash, which is a very different situation. Any questions about this? Now the next topic, so this was 6.2. 6.3, we've talked already quite a bit, so let me just quickly summarize. This has, of course, to do with garbage collection. And you have written programs that allowed you to explore the wonders of garbage collection. The upshot here is primarily that the complexity of garbage collection, which is essentially necessary because we have memory fragmentation, and we've already seen that if you want to allocate an array, for instance, that array has to be allocated in a contiguous chunk of memory. And so if your memory is fragmented so that all the little fragments are too small to allocate the array that you want to allocate, you actually have to carry out a garbage collection, and which is essentially the compactification of the memory that is available. So if you have many, many different small memory pieces, then they basically have to be combined into one big one, which means you have to move stuff around. And that, of course, implies that the complexity of garbage collection is proportional to the size of the memory that you are dealing with. So the overall idea that people have, well, I am going to use a bigger memory. I buy another 16 gigs of memory, and so I'm going to escape the ravages of memory fragment of garbage collection. That's really not true. What happens is if you have a bigger memory, you are probably going to reduce the amount of instances where garbage collection has to be applied. But whenever it does happen, it will be much more painful, because now the amount of memory that you have is much, much bigger, and therefore the time that it takes to compactify the memory that is now fragmented all over the now more than 16 gigs is going to take a lot longer than if you had only 2 gigs or something like that. So it really is the kind of thing that doesn't have a good solution. Okay, usually in many other instances, the problems that we've encountered, there are ways of working around them. You will not be able to avoid garbage collection. Garbage collection is simply a part of what happens when you have dynamic data structures, And that is a bullet you just have to bite. The main issue here is, of course, that you have to understand that it will happen and that it will take time that is proportional to the amount of space that you have available. And that means that if you have more space, the garbage collection will take longer. Any questions about that? Now, we've already talked extensively about parameter passing, and so the next topic that I'm going to deal with is our language properties. So this is 6.6, language properties. And the first one that I'm looking at is initialization. If you allocate a variable, and that of course is usually called, you declare a variable, you effectively instruct the compiler to set aside memory for that variable. Now, for simple variables, that's not particularly interesting, but if you want to declare an array, maybe a 100 by 100 by 100 three-dimensional array, well, you're looking at a million elements, and depending on how much space you need for each element of the array, you may need a megabyte, or you may need 4 megabytes if you have a word of length 4 bytes, or whatever. So when you do that declaration, you basically say, this is the structure, this is the array that I will use in my program. And now the question is, will these elements be initialized? We've already allocated the memory for them, but now will they have values? And if so, what would those be? And so we have 3 different ways of dealing with that. We have undefined, we have predefined, and we have unspecified. Now that doesn't tell you much, so let me explain how this actually works. The one that you know probably best is predefined. You effectively assign an arbitrarily chosen value, or your compiler does assign an arbitrarily chosen value to the elements at hand. In the case of C, for instance, that would be 0. So if you declare a simple variable, then it initially will be initialized by your compiler to have the value 0. If you have an array, then all the elements of the array will be initialized to be 0 in C. Now that, of course, means that there is a cost that is being incurred. The cost is the initialization. If you have an n by n array, then the cost of assigning 0 to the elements, the n squared elements of that array, is n squared. Whether you are really interested in that initialization or not, is immaterial. You are going to pay for that, assigning 0 to all the elements of the array. Now, the second, in this list, the first, but the second one that I'm going to cover is undefined. Undefined essentially means if you declare an element, a variable, then it is tagged with the tag undefined, meaning you have not assigned a value to it. It has not been defined yet. So in this particular case, the presumption is that if you want that variable to have a particular value, you have to assign it explicitly to that variable. If you don't, then it is considered not to have a value. It is undefined. Now, this again incurs a cost. The cost is that you are paying for the initialization of the variable with the value undefined, with that tag. And so in this case, this will cost about the same amount of time as the predefined. It probably could very well mean that you're going to have an additional space cost. There may be a bit that has to be set with that tag. That's how it is implemented is not that important. But there are programming languages and compilers that insist on that implementation. And if you have an array, n by n array, that has n squared elements, then the time that is required to initialize the elements of that n by n array to be undefined is again in order of n squared time. The third possibility is unspecified. That means that whatever garbage is sitting in that memory location is going to be used. If you didn't assign anything to it, the program will simply take whatever garbage is sitting there and use it to do whatever calculations you carry out. Now, you probably will say this is a horrible idea. This is terribly unsafe, and it is not the kind of thing that you would ever want to consider. And I would disagree. I view predefined, the kind of thing that you're used from C, for instance, as much worse than unspecified. My personal preference is for undefined. Now, let me tell you why. The fundamental issue here is that ultimately we are looking at trying to come up with a correct program. Now, in order to have a correct program, we want to make sure that we detect errors. And there are two types of errors that we have to consider. The first one are syntactic errors, errors that can be detected by a compiler, or a runtime error that will simply be detected without requiring any analysis. Semantic errors, on the other hand, are errors where we're getting something, but it is wrong. So for example, to give you a very, very trivial example, suppose you count things. And you have a variable that counts stuff. And if counting starts with 1, then you probably want to initialize that variable to 1. Now, that, of course, means that you actually have to do an assignment of 1 to that counting variable. If you forget to do that, and you happen to use C, then that variable will have the value 0. And so that means that now your count is off by 1. Which means in the final analysis, whatever you compute using that count variable is going to be wrong. The problem is that this is kind of difficult to detect unless you have a very small sample where you don't really count to large numbers. If you have a very large set of things to count, then kind of difficult to determine whether that is correct or not if it is off by 1. Now, if it is undefined, then obviously you will find out that you're using something that hasn't been defined yet because you didn't assign the value 1 to your counting variable, and so that will be immediately detected. Now, what about the third one, the unspecified, using whatever garbage is sitting there? Well, in that particular case, which of course, as I said, is the cheapest of the 3 methods because you don't have to assign anything to it. It just happens, you just use whatever is sitting there. If that's the case, then you can do the following. You run the same program with the same input twice. If you get different results, then that is a clear indication that something is wrong. And what is wrong is, of course, that this unspecified value differs from one execution to the next one, even though you're using the same program with the same input, because most likely there's different garbage going to be sitting the second time around from the first one. And so in that case, you actually will find out fairly easily that something is seriously off, because the garbage that you're using is going to be different from the first run to the second run, and that means that now you have a clear indication that something was wrong, and that something that was wrong was in fact a semantic error. You failed to include an initialization, which of course is semantic rather than syntax, but it can be detected in a relatively syntactic way rather than a semantic way. So in that sense, the fact that we are looking at a clearly unsafe situation, namely using whatever garbage is sitting there in that memory location, is actually going to be safer than the predefined situation where, in essence, we are looking at a value that is predefined, but may not be what it is supposed to be. So in this case, as I said, if we count starting at 1, then obviously if we forget to assign 1 to that memory location, the count is going to be off by 1, which is going to be consistent. So if we run the same program a second time with the same input, we're going to get exactly the same output. It just happens to be wrong. In the case of undefined, which to some extent is the most straightforward one, even though it makes it relatively complicated to implement for the compiler. That's why most compilers don't do that. But logically, it is, of course, the most straightforward one. If you want a variable to have a value, then you better assign that value explicitly to that variable. If you don't do that, then it does not have a value. It is undefined, and that will then immediately result in a crash if you actually try to use it, because it is undefined, and if you use something that is undefined, then it will not be acceptable and the program will not continue. So personally, as I said, I would say undefined should be your best bet, unspecified actually a second bet, and predefined, as far as I'm concerned, is the worst of those three. Once again, of course, I'm on the losing end of that equation, because that is what seems to be what is happening for the most part in our programming languages. So swimming against the stream. Any questions? Okay, so we're going to go to the next topic, which is packed arrays, packed data structures. And for the most part, we're going to really look only at arrays. Why? Because arrays are the kind of data structure that can be easily specified to a very large size. If you are going to define a linear list, well, you're going to actually construct that linear list. And that will take a certain amount of time to construct it. If you declare an array, well, you can easily declare that array to any size. So if you want 1,000 by 1,000, you just say A 1,000 by 1,000, and you have 1,000,000 elements in your array. So now the question then arises, what is it that happens when we have, say, a Boolean array? Well, obviously, in a Boolean array, we need 1 bit per element. But in fact, in most implementations, if you have a Boolean array, the program is probably going to use 1 byte. Which means that 7 out of those 8 bits of that byte are going to be wasted. So that means that one might be concerned about that waste. The next example, I mean, if you think that a Boolean array is not that interesting, let's take some 3-valued variable. So it can take 3 values. And that means that even if we do it the most efficient way possible, we're going to use 2 bits to represent something that can take 3 values. We obviously need at least 2 bits to do that. And let's just assume we do it with 2 bits. Well, that, of course, still means we're wasting at least 25%, because with 2 bits, we could actually represent 4 things, not just 3. So if we allocate 2 bits to represent something that has only 3 different values, we effectively are wasting 25% of the capacity of representing things. So if we look at that 3-valued thing, if we have 1, then we need 3. If we have 2, we need 9. 3 would be 27. 4 would be 81. And 5 would be 243 different combinations. This is 3 to the 5th. And so this is reasonably close to 256, which is 1 byte. So we could actually pack 5 3-valued items into 1 byte, which is clearly more efficient than using 1 byte for 1 3-valued thing, or even 1 byte for 4 3-valued things. So obviously now we have to look at what it is that is involved here. Let's just take the simple Boolean array. So we have, say, B1 through N. So we have, there's a B1 through 8. So that would be byte 1. And then 9 through 16, byte 2. And so say we go to 1,000, so this would be byte 125. So we have a packed array PB with 125 elements, each being 1 byte. And we have in our program, of course, B. So we have BI. BI would be what we're going to use in our program. But then if we pack that B into PB, then we're going to use, instead of 1,000 elements, only 125 elements in PB. And both of them are now byte-based, except, of course, B is going to use only 1 bit of each byte, whereas PB is going to use all 8 bits of each byte. Now, in order to go between B and PB, there's work to be done. If I want to know what BI is in that representation through the packed array PB, then essentially I have to do 2 things. I have to do I divided by 8, floor of that. That will give me the address in PB. So this gives me the byte in PB, and then I have to do I mod 8. In this case, we'll assume everything starts at 0. I mod 8 then is going to give me the bit, the number of the location of the bit in that byte in PB that corresponds to BI. So clearly there is work to be done. This isn't a totally trivial exercise to find what BI is, because we have to first locate the byte in PB. This is the number, the index in PB. And then within that byte, we have to locate the bit that really corresponds to BI, and that is within that byte has the number I mod 8. So that is a mapping that is not entirely trivial, and obviously if you're looking at the 3-valued example, then this is significantly more complicated. But it is certainly doable. In this case, you're basically mapping 5 elements into 1 byte, and here it is 8 elements into 1 byte, and then you have to do the address calculation. First, what is the index in the packed array, and then you have to look at that byte and determine what it is. And so this is a little bit more complicated here, but it is still quite doable. And so now the question then is, should we pack? So we're going to assume we have an array A, which is unpacked, and we have an array PA, which is packed. And now we want to determine, do we actually want to pack? And so there are 3 cases that we have to distinguish. The first one is A fits into main memory. Well, in that case, there is no point in packing, because packing requires carrying out that mapping function. Since there's nothing to be gained because the unpacked array fits into main memory, we can save ourselves that packing function to be executed, because there is nothing to be gained from that, because A fits into main memory, and we don't have any problem because of virtual memory management. So the second case then is A does not fit into main memory, but PA does. In that case, it is obvious that we want to pack, because the fact that PA fits into main memory means that we don't have to invoke virtual memory management. And that, of course, is the big issue, because virtual memory management, as you have found out, is not terribly efficient. It takes orders of magnitudes more to fetch a page from external memory. And so if we can save ourselves that overhead, then we're certainly going to come out ahead, even though we have to do some additional work. Namely, we have to carry out that mapping function from packed to unpacked, and from unpacked to packed. But this is still, this is a few operations per access, which is dwarfed by the cost of virtual memory management. So if A does not fit into main memory, but the packed version of A does, then it is quite obvious that we should pack. The third case is neither A nor PA. PA fit into main memory. Well, in that case, it turns out that we actually have to do more analysis. You might conclude that, well, we're going to put PA into main memory. I'm sorry, we put PA, we use PA because there will be fewer, yes, both of them will have to be in external memory, but there are obviously fewer pages to be retrieved if we have PA than if we have A. But that may not be true. How can that be? Well, it depends on the access. If the access is random, so that if we have PA for every access to PA or A, we need to get a new page for PA, and obviously also for, if we do it with A, for A, then we are really not saving anything. So if the axis is random and a new page per axis, then do not pack. Because whether we need a new page for PA or a new page for A, we have to retrieve that page, and depending on what it is, that mapping function still, the packing function still has to be carried out if we pack. So in that case, we are better off not doing that, and so we just do not pack. We just use A because we still have a new page for each axis. If the axis is 1, 2, 3, 4, and so on organized, then in that case we pack. Because in that case, we're going to have fewer pages that will have to be retrieved if we do PA than if we use A. And so what that really then means is if neither the unpacked nor the packed array fit into main memory, we have to do significantly more analysis in order to determine how the access is carried out in the program. And if the access is organized, say, go through the entire vector 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, then of course we will need fewer pages for the packed array than for the unpacked array, and therefore we should pack. On the other hand, if the axis is random, we get an element and then we get another element, and that other element is in a different page, regardless of whether we're talking about A or PA, then obviously we are not gaining anything by packing, but we're losing something because we still have to do the unpacking, which means more work. And so in that case, one should not pack. So that then sums up what happens when you do packing or not packing, because it is not entirely obvious how all that has to play out. It turns out to be much more complicated and requires much more analysis than you might have initially thought. Any questions?
I've got a quick question.
Yes.
So on case 3, with the random access pattern, what you're saying is that since it's going to be a new page, presumably whether it's A or PA, then the overhead incurred by using PA is not worth it, and so we should just not pack.
Well, you're not getting anything out of PA.
Should we be considering any space complexity concerns?
Well, no, you don't, because in that case, we're assuming that your external memory is sort of unlimited.
Okay.
Okay? And so the question really is not the space that you need to store A or PA. The question is, how many pages do you have to get in? That's really the ultimate issue here. And if you have random access, so you will need a new page whether you use A or PA, then you're better off doing the least amount of work, which is A.
Okay. I was just thinking in the case of where like PA barely doesn't fit into main memory. So for example, yeah, you would need to page, but it'd only be a low number of pages total.
Well, yes. I mean,
maybe enough to fit in the active memory set, something like that.
If it's barely fitting, then you still have, then you have to play a probability game. But if if both of them are way off, then clearly you're better off not packing.
Okay, so the third case is more for the assumption that they don't fit by a wide margin.
Right.
Okay, awesome, thank you.
I don't really want to say it that way because it really comes down to the question, do you need a new page every time you have an access? And that could actually be, even if 99% of PA fit into main memory, into the active memory, and only 1% doesn't. But if it is so that you need a new page every time you have an access, then it doesn't really make much difference whether you barely fit or not.
Oh, okay. Yeah, that makes sense.
Okay, so it's actually quite tricky. Any other questions?
I want to say no. I think putting random cards in my deck would be bad.
Well, you might get the blade. You might be able to do blade twice.
Yeah, but
All right, then you have your exam on Wednesday, and then we'll continue on Monday with lazy evaluation. Okay. Bye-bye.
Can you please explain the exam really quick?
What do you want to know
Like
about
how
it?
it's structured, how we need to go about it, that sort of thing.
You basically will be sent by email the questions. You probably should log on by about 3 o'clock.
It is Monday.
You have until 5:15. The questions are the questions that I had originally scheduled for an hour and a half, so you'll have more time. The submission of your answers is going to be exactly the same way you responded for assignment 2, so you just come up with a file and you mail it in. Okay. Does that answer it?
Yes, it does. Thank you.
All right. Okay. Bye-bye. Talk to you
Bye.
on Monday.